Fantastic, thanks. Thank you, Sarah. So hopefully people have had a bit of a look at this chemical structure, and depending on your background, you've either been utterly horrified and immediately understood what lots of the problems are, or like me, you sort of peered at it a little bit and you thought, that probably doesn't look quite right, or that doesn't look quite right, or maybe you've got absolutely no idea as to where to start. So the reason that I thought it would be a good idea to explore this particular topic is that, of course, biomolecular simulation, the really brilliant thing about it is how multidisciplinary it is. So you obviously need to know about biomolecules. You probably need to know a bit about physics because we're using an algorithm. So Edina's going to talk about that later. And of course, also you need to know about computing and scripting. So all of these different things. So depending on what your background is, some parts of this you might find easy and other parts you might find difficult. So I'm a theoretical physicist. So the parts I find really difficult about biomolecular simulation are the chemistry. So that's why I've decided to give you my sort of outsider's view on what the common pitfalls associated with difficult chemistry are and how you might avoid them, and definitely when you should ask for help. So if you have questions during the talk, then do feel free to ask questions during the talk. I think, Sarah, will you be able to see the chat? Yeah, okay, so Sarah will be able to see the chat and she'll be able to say, oh, Sarah, there's a question. So do feel free to ask questions throughout the talk. So this is very much an informal session, and it's really my opinion on what I think would be helpful for you guys to think about. If you're already a chemist, then please do feel free to smile wistfully about all of the problems that us non-chemists experience. So this talk is called, let's go back to the title slide if I can, Crimes Against Chemistry and How to Avoid Them. And it's written by me, a theoretical physicist, but I'm very fortunate in that I'm married to a medicinal chemist, an organic chemist, Jeff Wells, and I promise you he has checked it. So hopefully all of the mistakes are going to be in what I say, not what's on the slides. Okay, so actually Jeff took this picture of caffeine near where he works at UCL in London, and he was so horrified by it that he uses it in all of his talks. So for those of you who have had a go, here is actually the structure of caffeine written out, even with all of the hydrogens. So we can see that there are some problems in this structure. So first of all, nitrogen probably doesn't like to have this many bonds. It's a bit upset, this nitrogen, that's not chemically correct. And probably carbon doesn't like to have 5 hydrogens attached to it. So this is obviously not right, this group here. Also, we're missing a methyl group from this nitrogen. That isn't so much a problem with the chemistry, it's just actually the wrong molecule. And there's also something a bit funny going on here with this angle. So there's all sorts of problems associated with this structure. And if you see them immediately, you're a chemist. And if you don't see them immediately, then you know that these are things that you need to think about very carefully. So this nice structure of caffeine that Jeff drew for me in ChemDraw is actually, unfortunately, not often how a chemist would represent it. So if we just look on the next slide, so this is the structure of caffeine. So this is the structure of caffeine that Jeff drew for me, but this is how he would normally draw it. So you notice that the chemists don't bother putting the hydrogens in. And that's because to them, it's so obvious where they are, you don't really need them. And also you'll notice that here in the structure written out in full, this dash here means that there's a carbon, a methyl group. So it's attached to a carbon and then 3 hydrogens, but the chemists don't bother to represent that because they think it's so obvious. So these are the sorts of things that make it more difficult for non-chemists to understand these chemical formulae. And so now we have on the right-hand side structures of caffeine in 3 dimensions. So these are sort of, these are actually, of course, just 2-dimensional representations of the molecule. And we can ask ChemDraw to make us a 3D representation. And you'll see that there are these dashed lines in here. That's very important. Well, that means that this is a sort of resonance structure, and we'll talk about that in a minute. And then the other version I've got here is a structure that I made in from a PDB file in Chimera. So this is quite good because, of course, before I made this, I could rotate it around and look at it. So the reason I've shown you these structures is that if you are a non-chemist and you're trying to understand what these chemical formulae mean in terms of your atomistic structures, one of the things that I have done in the past is got the chemical structure in front of me, looked at the PDB file in VMD or Chimera or Pymol, and just tried to work out what the correspondence is between the two. And I found that very, very helpful to do, to try and help you really see how many bonds there are and what all of the atoms are doing and what sort of interactions they're participating in. If you're a chemist, you can just look at something like this and know it's right. If you're not a chemist, then you probably need to have the 2 formula next to each other and try and rotate it and understand what you're seeing. So, of course, a lot of our structures that we use for biomolecular simulation come from this amazingly wonderful resource, the Protein Data Bank. And I understand that yesterday there were, that you received, for those of you that were there, you received some amazing advice from Andrea and Martin about how to make sure that your PDB files are good, that you're using for your simulations, because if you start off in the wrong place, then obviously you probably won't end up in the right place. So you need to be very careful. So I just want to offer a few more bits of advice for people using the PDB for biomolecular simulation who aren't necessarily chemists. So just to point out, as you would have learned yesterday, that unfortunately, because biomolecules are so complicated and it's so hard, of course, not all structures in the PDB are perfect. And one of the situations in which we experience particular problems is with ligands, so with small molecules. And of course, very often we're doing biomolecular simulation because we want to understand how a drug interacts with its target. So if we go to the PDB and the ligands that we're downloading aren't quite right, then those need to be fixed, and those are going to cause problems with our simulations. So I've just pointed out these 2 papers here. This one is a bit more recent, the one at the bottom, just to show you that actually you need to be very, very careful when you download structures from the PDB, especially if they contain non-standard groups, just to make sure you're really happy with the chemistry. Okay, so what I'm going to do now is I'm going to go through all of the possible mistakes that, well, all of the many mistakes that I've made, probably not all of the mistakes that I've made, but certainly the worst of the mistakes that I've made in the past, and just sort of give you some tips about how to avoid them. And I'm going to start them off with what I consider to be the most serious first. So the most serious mistake that you can make in chemistry is having is atoms having the wrong valency, which means that they've got the wrong number of bonds, the wrong number of covalent bonds. And of course, this is a complete and utter disaster. So certainly, I mean, I'm an Amber user, and I would thank Amber developers very deeply for the fact that actually they're very, very, very strict about chemistry, and they won't often let me make these mistakes. So if I read something into Amber that's got the wrong number of bonds, most of the time Amber will tell me, and it won't let me build it. I understand that with some other codes, maybe commercial codes, that the customer is always right, and these codes are maybe a bit more forgiving. So in which case you need to be extra careful. Certainly Amber will tell me if I build something that's really terrible, but maybe some other codes don't. So it's extremely important to understand how many covalent bonds each atom should have in your system and why. And of course, the most basic idea is all to do with, you know, sort of school level chemistry. So how many valence electrons all of the elements have, and how many they would like to obtain in order to fill their outer shells. So hopefully everybody remembers this sort of picture from chemistry. So here's a single covalent bond, a double bond, a triple bond, and bonds can be ionic, they can be covalent. And this one, a coordination bond, is where an atom has a lone pair, so an unpaired pair of a pair of electrons that it can actually stick in to an empty orbital of another atom. And the reason I've included this one is because it's important for some of the metal interactions that we're going to talk about right at the end. So most of the time, this school level chemistry is sufficient. So you know that, you know, hydrogen should have one bond and carbon should have 4. But that's not always the case, as I'll describe in a minute. So the other things that you need to be aware of that might cause you problems with valency are missing residues in your PDB file. So you need to check for those. I'm sure you've heard about this before. So, you know, not all of the residues appear in the protein structure. And the other thing that you need to remember is that if you've got cysteine residues, and if they're really nearby in your structure, they'll probably need to be covalently bonded. And depending on what simulation software you're using, you might have to put that bond in by hand. In Amber, I put in that bond by hand. So you need to be careful of that too. So when we download a structure from the PDB, depending on whether we're downloading an NMR structure or an X-ray crystal structure, they're going to look very different. So I've provided an example of an NMR structure on the left and an X-ray crystal structure on the right. There are more crystal structures in the PDB than there are NMR structures. NMR is extremely hard, and it's generally only applicable to smaller proteins or protein complexes. So there are fewer structures in the PDB that have been deposited that have used NMR, but NMR structures have the hydrogens. Crystal structures do not have the hydrogens. And you can hopefully see that difference in the two pictures. So this one on the left, hopefully you can see at a glance, it contains far more atoms than the one on the right. So there are normally about, you know, when you add hydrogens to a protein, you generally, as a rule of thumb, you double the number of atoms in the system. The other thing that you will notice about the crystal structure that's not true for the NMR structure is that there are these lots and lots of little red blobs all over the place. What are they? Well, they are the crystalline waters that have crystallized with the protein. And of course, you can only see the oxygen because there are no hydrogens in crystal structures. So you will need to decide before you run your simulation which ones of those, if any, you're going to keep, and which ones you're going to discard before starting your simulation. And when you look at your crystal structure as well, the PDB file, you may also discover that there are other sort of bits and pieces lurking in there, which might be come from the media used to crystallize the protein and things like that. So do inspect what's in your PDB file very carefully when it's an X-ray structure. The other thing you might notice about the NMR structure is not only are there more atoms, there seem to be more conformers. So NMR gives you an ensemble of possible structures, which is very nice. So it gives you some idea potentially of how flexible the system is and where. But of course, if you're going to run a molecular dynamics simulation, you want to start from one of those structures, or you might want to set up an ensemble of simulations where you start from each of the different NMR structures in the ensemble. So you'll get different information in your PDB file depending on whether it's an NMR structure or a crystal structure, or increasingly now a structure from cryo-EM or cryotomography. So we need to think, if we're using an X-ray structure, we've got some work to do to add the protons before we can start our simulation. Adding protons is not entirely straightforward. And that's because amino acids are what they say they are. They can be acids. And they have titratable groups and what we call pKa shifts. So if you have, for example, a residue that if it loses a proton can form an extra hydrogen bond, you will find that the pKa of that residue is shifted from what you would expect it to be if it was just floating around in solution. So we need to take this into account when we're protonating our system. Otherwise, we're going to put protons in the wrong places, or protons will be missing where they should be. So the amino acid that causes the most problems is histidine. And the reason that histidine causes so many problems is because it has a pKa of about 7. So actually you don't really know what protonation state it should be in. And so certainly amber, which I use, makes you make a decision so that it knows that you've actually thought about it and interacted with it. And we do this by changing the residue name to correspond to the correct protonation state for a particular histidine. Now, one way of doing this, and this is the sort of method that I would recommend, is if you're protonating your protein, then use a tool, a protonation tool such as H++. And the reason that I recommend this is that H++ will think very carefully, not just about your amino acid and what protons it should have when it's isolated, but it will take the protein environment into account when calculating the pKa of each of your amino acids. And so it will decide, it will make a better decision about what the protonation state should be. And then, of course, what you want to do is once you've protonated your protein with H++, or a different code for, oh, I've got the chat. Aha, yes, Sarah has correctly pointed out that there's a really, really good workshop on protonation states and pKa. Thank you, Sarah. So what I do when I've protonated my protein is I protonate it sort of naively, you know, not using, not taking the environment into account. And then I compare where the protons are just to see if there are any surprises. And of course, that you can learn quite a lot from that, because you're learning how your environment is affecting the chemistry of your system. And if there are pKa shifts, they could be functionally important. Now, if you're interested in protein ligand interactions, then of course your ligand will probably not be protonated when you download it from the PDB if it's a crystal structure. After having checked the chemistry very carefully, then you'll want to add protons. Now you can do this with OpenBabel, which will do this for you. H++ won't work for ligands. I'm not sure about ProPKA, but what my advice to you is, if you're not a chemist and you're protonating a ligand, please ask a chemist, because it's very, very easy to get these things wrong. So I would suggest, if you're working with ligands, make sure you've got a friend who's a chemist, just so that you can ask him or her if you're on the right track, because they will see things immediately that you can't. Oops. Okay, so here's a situation where the chemistry that you have done at school doesn't give you enough. So there are extremely important examples of what we call resonance or aromatic structures in biology, and these result in planar rings. So what happens here is, so this is the most simple example is benzene. So what happens is the shape of the benzene ring allows all of these pi electrons above and below the ring to interact with each other and form this big donut of delocalized charge. And you might see that chemists draw like little circles in their ring structures, or you might see these sort of dashed lines, and that generally is there to indicate these resonance structures. And that means that the electrons are completely shared between all of the atoms in the ring. So the first thing that this does is it makes sure that the ring is completely planar, because of course, if any of these atoms deviate away from the plane, this will affect all of the way in which these pi orbitals can overlap, and it will break this delocalization, and that's extremely energetically unfavorable. The other thing, and this is probably the most important to us, the other thing is that these sorts of aromatic rings, because they've got these two massive donuts of charge either side of the ring, these love to form van der Waals stacking interactions. So these stacking interactions are particularly important, for example, in DNA. And they're important in things like tryptophan and these sorts of amino acids. So these big clouds of electrons are also polarizable, so they'll like to stick to a positively charged ion as well. So this type of chemistry changes the physical interactions that your system is going to adopt. So also, chemistry constrains the peptide bond to be flat. So if we look at, this is a very, very simple peptide here. And this bond, this is the peptide bond. So there is resonance across this peptide bond, which means that it just cannot rotate, because that will break the interaction with those pi electrons. So this means that this angle omega here is completely fixed. The two angles that can rotate are theta and phi. And these angles, the rotation of these angles, is of course what which enables us to plot our Ramachandran plot, where we have allowed regions of protein structure. If there was no resonance across this bond, then proteins would be very, very, very different. And certainly one of the things that we would need is we would need a sort of 3D Ramachandran plot, because this bond would also be rotatable. So in this instance, actually having a flat ring means that we only need to worry about sine thigh angles in proteins, because this is absolutely rigid, can't rotate. Okay, so I'm a theoretical physicist, right? And everything in physics is symmetric. The only thing in physics that isn't symmetric is the second law of thermodynamics and the Big Bang. So, I mean, I find anything to do with chirality impossible. So this for me is the sort of chemistry violation. It's a bit like, you know, jaywalking in America. You know, it's almost impossible to avoid making a mistake, and half the time you don't even know that there's a mistake there to be made. So be very, very, very careful with chirality. Fortunately, most of the molecular building tools will take care of the chirality of amino acids for you. So probably you'd have to try very hard to make the wrong one. Nevertheless, if you're doing anything that's not relying on a previously defined template for a residue, be very, very, very careful about the chirality, because it's extremely easy to get wrong. If you're not a chemist, I mean, maybe this is a very controversial thing to say, right? But if you're not a chemist, or you don't have a best friend who's a chemist, do not work on sugars. Sugars are a nightmare. They're absolutely, completely and utterly horrendous. So just to try and talk you through this a little bit, why sugars are so bad and so difficult to work with. So on the right hand side is a picture from the Glycan website. So fortunately there are tools for building sugars, and I would say that given the complexity of the problem, they are extremely usable and really awesome. Given that, if you've got something extremely difficult to do that's very, very complicated, even the best piece of software in the world isn't going to get it right for you. You need to know about it yourself. So on the right hand side here, this sort of magenta picture is what I did, you know, it's on the Glycan website, because it's the spike protein from SARS-CoV-2. And one of the mistakes that is commonly made is forgetting that a lot of proteins, and the spike protein is a particular example, are glycosylated. They're covered in sugars. So that's one thing to really, really be careful of when you're thinking about whether or not you want to simulate a particular protein. If it might be glycosylated, then you want to probably get expert help if you're not a chemist. So just to show you how horrendous the situation is, this is a screenshot from the Glycan building tool. Okay, so you first decide, okay, so I'm going to build a sugar. Is it going to be a mammalian one or a bacterial one? There are different options for the two, because bacteria and eukaryotes have got different bases of sugar. So first of all, you have to choose which sugar you want. So this is there's this big choice of monosaccharides here. So you have to choose one of these. Then you have to choose whether it's an L or D isomer. So you have to think about the chirality. Then you have to think about the ring type. Then you have to think about the configuration, and that's which bits are sticking up and which bits are sticking down. And then you have to join it onto the next sugar. So then you have to think about which place in the ring you're actually attaching it. And at each one of these stages, you can make a horrible mistake and get it all wrong. So my advice to everybody, controversial though this may be, is please beware of sugars. If your system contains sugars, ask a biochemist. So if you're working on a system that you're looking at its atomistic structure and you're downloading the PDB file, there will be biochemists out there who also do experimental assays on the structure that you're interested in, and they will know whether it's glycosylated. They might also tell you about other post-translational modifications that might be present. So for example, many enzymes like to be phosphorylated, and that switches interactions on and off. As I've said, things can be glycosylated. There's a possibility that proteins can be ubiquitinated. So protein ubiquitin tags are added to molecules to say, right, throw these away now, stick them in the bin. Another thing to be really careful of if you're working with membrane proteins, which are another area of difficulty. If you're working with membrane proteins, then sometimes your protein can have a fatty acid covalently bonded to it. And there are all different flavors of fatty acid conjugation to proteins, normally membrane proteins. Fortunately, because I don't work on membrane proteins, so that's fine. So it's a very, very good idea to have some contact wherever possible with the experimental teams that work on the system that you're interested in, because that will give you a broader appreciation of how relevant the PDB file that's being deposited is to the actual function of your protein, because there might be bits missing that really matter. Okay, so I call this high-level criminality. So this is the sort of criminal behavior where you're probably doing some sort of high-level financial fraud that involves shell companies and all of this sort of thing, Russian oligarchs and stuff. Because actually, if you're doing anything with metal ions, you're doing something in biomolecular simulation that I would consider to be advanced. So this is probably now my favorite protein, and Edna and I work on this protein together. So Edna leads the team who work on this protein. So she introduced it to me, and she's going to be talking at 11 o'clock. And so I wanted to use this example. So this is the helicase from SARS-CoV-2, and it's the motor that pulls the RNA out of the protein, of its sort of protein shell when it's packaged, and it also helps with the replication and transcription and error checking machinery of the protein. And what we can see here in the middle is a magnesium ion, and this magnesium ion is essential for the catalytic function of the enzyme. This thing here is the ATP fuel. And you will notice that there are all of these water molecules around it, and also a serine residue. When you have metal ions in proteins, they like to have coordinated bonds. Now, magnesium's a bit different because magnesium isn't chemically coordinated to the waters and the ATP in a formal sort of covalent sense. But the electrostatics are so strong that in almost every crystal structure you ever see, you always get the same arrangement of chemical groups around the magnesium. And for example, these oxygens are always, I mean, literally always 2.1 angstroms away from the magnesium, and you see that everywhere, not just in this structure. You see it in lots and lots of crystal structures involving ATP and an enzyme and magnesium. So if you're going to run a simulation of this thing, you're going to have to build these water molecules in, and you're going to have to make sure that the chemical groups are pointing in the right direction towards your metal so that the interaction is represented. So if you're very lucky, different situation. So this is also our SARS-CoV-2 helicase, but now this shows the zinc binding sites. So these pretty purple colored atoms are the zinc atoms. And in this case, there is actually a formal covalent bond within our representation, between the zinc and these nitrogens and the cysteines. And that is because the zinc likes to have lone pairs donated into its empty orbitals. It really, really likes that. And so it really is a covalent like bond in this situation. And what's quite complicated, of course, is when you're looking at these type of zinc interactions, the zinc will interact generally with histidines or cysteines, but of course in this one you've got 2 histidines and 2 cysteines. In this one you've got 4 cysteines. In this one you've got 1 histidine and 3 cysteines. So in every single case when there's a zinc, somebody, ideally a chemist, has to look at the structure and say, okay, which of these residues is doing the coordination and which one am I going to say is actually the sort of covalent linkage that I'm going to impose in my simulation. And when we built with Edina the full replication transcription complex, there were about 13 of these, and each one of them had to be looked at by hand, and each one of them has 4 interacting residues, and each one of those 4 interacting residues had to be identified. So this is not a high throughput situation. And also, of course, in the crystal structures, these quite a few of these structures that we're looking at now actually come from cryo-EM rather than from crystallography. And if you're looking at a cryo-EM structure, it might be that maybe not all of the groups that you think should be coordinated are pointing in the right direction towards your zinc, and then you might have to go in and rotate the side chains because the people who solved the structure might not have considered that before they deposited it. So be careful. I had to show this PDB file because I just think it's so wonderful. This is just, if you see something like this, then you're very, very, very lucky. So this is actually, I'm showing off a bit because this is a crystal structure from my friend Richard Bayliss at Leeds, and I just think it's absolutely wonderful. So if we zoom in on the active site, it's a kinase. This thing is a kinase, so it's a metabolic enzyme. So if you zoom in, you can see, so here are the 2 magnesiums. So there are 2 magnesiums here. I'm terrifying, but there are 2 magnesiums, and they could actually see every single coordinating water surrounding these magnesiums in the crystal structure. So if you're in that, I mean, it's 1.7 angstroms, right? If you're in that situation, you're really, really, really lucky. But unfortunately, most crystal structures will not be this clear cut, and probably most of the waters will, not all of the waters will be there, and you'll have to think, do I have the right number of atoms around my metal, and do I need to add more waters, for example? But this one is just gorgeous. I picked out this one as well, just to say that it's not always magnesium and zinc. This one is another metabolic enzyme. It's the enzyme responsible for cutting off the first amino acid of every protein, because the start codon is always the same amino acid, methionine. So, and this one actually in here, these 2 atoms are cobalt. And you'll notice that again, there's this very special arrangement of groups around the cobalt atoms. And then just to scare everybody, this is photosystem 2. So I had a look at photosystem 2, and this has got all sorts of metals all over it, as you might expect. Here, the magnesium is in these interesting ring type structures. We have a manganese here, and of course we have iron. So in something like the photosynthetic reaction center, there are lots and lots and lots of these different metals, and every single one of them needs to be considered properly, and you need to think perfectly about each one. And notice that this is only 4.5 angstroms resolution, right? So you're probably going to have to really think carefully about some of the chemistry if you're going to get it right, because it's not going to be in the crystal structure. Okay, solvent. So on the left-hand side is one of my pictures of DNA showing the counterions and the water. So if you're running a simple simulation, normally solvating it is not too much of an issue. You need to have a sensible salt concentration. So we normally neutralize our system, and then we add the equivalent of 150 millimolar of positively and negatively charged counterions. Normally, for the positively charged counterion, we use either sodium or potassium, and we always use chlorine for the negatively charged one. Sometimes we use calcium, normally only when we're simulating DNA. I have to say that using divalent ions is different, and you need to think about that very carefully, because they're so highly charged. A divalent ion, the charge density is so high, you need to really think carefully about how you equilibrate your system. So on the right hand side is the only membrane protein system I have ever built. It's an interesting experience to go through. Membrane proteins are special. If you're going to run simulations of membrane proteins, you really should make sure that you have access to specialist advice on how to do this. So there are all sorts of pitfalls. One of the most common ones is the fact that actually there is an amazing array of potential lipids that can be in a membrane. You have a huge possible variety. Many of them are biologically relevant, and knowing which lipids you should have in your membrane, how to equilibrate them, etc., is a special skill. So I would advise people not to work on membrane proteins unless they have access to specialist expertise. And then if you do, please work on membrane proteins, because they're really interesting and really hard, and of course absolutely extremely important. Okay, biomolecular interactions. So you really need to understand what types of interactions your protein and your ligand potentially, and your lipids and your surrounding solvent is going to want to make. And so there's a wonderful resource called the Open Drug Discovery Toolkit, and that very helpfully gives us a list of all of the possible interactions that might be of interest to us as biomolecular simulators. So hydrophobic contacts. So of course, you know, oil and water don't mix. Hydrophobicity is responsible for the folding of proteins. Hydrophobic contacts are key. This one, aromatic face-to-face. That's all to do with that those pi electrons that I was talking about earlier, and the fact that they love to stack next to each other. Aromatic edge to face. These tend to not be as strong because you've got the edge of the aromatic ring interacting with the pi electrons, so it's not as strong as face-to-face interactions, but nevertheless there's enough polarizable electron density in those pi electron clouds for this aromatic edge to face to be a consideration. Hydrogen bonds are of course absolutely critical to biomolecular structure and interactions. Unfortunately, many of the visualization tools, for example, VMD, offer you the option of displaying your hydrogen bonds so that you can see where they are. Salt bridges occur when you have positively charged residues interacting with negatively charged residues, or very strongly polar residues interacting together. And of course, these are very important in stabilizing proteins. And then we have salt bridges with metal ions. Of course, they, you know, those can of course be critical, and those can also be important in deciding what solvent you might want. And this one as well, which I missed off the bottom, which is the pi cation interactions. So that's when you've got a big aromatic ring with lots and lots of pi electrons, and a positive charge really likes to interact with that. For example, arginine, because of these, because of the huge polarizable rings of delocalized electrons. So all of these possible interactions that are important in your system, and you need to learn to look for them, you need to learn how to look for them and how to see them in your structures. So DNA, I would say was a really, really good example of the types of interactions that you might want to think about. So here's the structure of double-stranded DNA. It's of course the perpendicular to the long axis of the helix. It's held together by hydrogen, very famous hydrogen bonding interactions. These hydrogen bonding interactions are so famous because they carry the genetic code. Also, if we look at this region of the molecule, we can see that the DNA bases are very, very snugly stacked together. And that's because they form these aromatic stacking interactions. And these are extremely important, in fact, as important as the hydrogen bonds in maintaining the structure of double-stranded DNA. So DNA is double-stranded because of a combination of hydrogen bonds and base stacking interactions. And of course, with DNA, you're also going to have to think about your solvent. You certainly need positively charged counterions surrounding it because the backbone is negatively charged. So, with DNA, I have actually run simulations with calcium as well as with sodium and potassium, and that changes the way the system behaves, can change the way the system behaves really very dramatically. Okay, so DNA, RNA. Now, hopefully people can see that the DNA and the RNA helix are different. So DNA has a B form helix and RNA has an A form helix. So the A form helix is sort of compressed, but more fat, so that it has a fatter twist. And the reason for this is that RNA has one extra OH group on the backbone, just one. That's 2 atoms, okay, just 2 atoms on the backbone. And this hydroxyl group is a nightmare. So I mean, I don't work with RNA when I can avoid it. I'll work with DNA, but I tend to not work with RNA. And that's because this extra hydroxyl group causes all sorts of problems. So it can form additional hydrogen bonds for a start. And so it's partially responsible for the fact that RNA can form all of these exotic folded structures that you don't see DNA form. This OH group also, this is not a problem for us as simulators, but it's a problem for the experimentalists. It makes RNA a lot more chemically reactive than DNA. But this extra OH group also affects the shape of the sugar in the RNA backbone compared to DNA. So the sugar has a different shape. It has a different pucker depending on whether you've got B DNA, or you can have A DNA as well. That happens when it's dehydrated. But you can have, but if this sugar changes shape and the hydroxyl group tends to make it want to change shape, then that changes the conformation of the backbone, and that is what is changing the nature of the helix itself. So the take-home message from here is that this tiny change, just the addition of 2 atoms, can have enormous consequences. So in this case, between DNA and RNA, they have the helices of different shapes because of this very, very minor chemical change. The other thing I would say about working on DNA and RNA is that every single backbone torsion has an allowed set of values. So and those are known, and you can plot them. So the chemistry is extremely well defined. And if you get it wrong in your simulation, so there was the DNA community went through a phase where when we ran simulations for too long, one of these torsions became distorted. This was known as an alpha gamma flip. And it took the community a while to get that fixed. So knowing about these details can be really important to knowing about whether your simulations are of sufficient quality or not. Okay, so this is again all to do with work that we've done with Edna and places where you can get help. So I've called this Neighbourhood Watch because it's extremely instructive if you're working on a particular protein ligand system or particular protein-protein interaction or protein-RNA interaction, to look at related structures in the PDB and see how close they are to yours. Because biology likes to use things again and again and again and again, and you can learn something about whether what you've done is correct or not based on whether or not it's been seen before. So this is work that Dennis did. So what we wanted to know for our helicase, at the time there were no available crystal structures for SARS-CoV-2 in the presence of RNA and an ATP. And so what Dennis did, and Majid and the rest of the team, is they went into the databases and they looked for every single structure that was a bit like ours. And they looked for whether or not it contains RNA. And then they looked for all of the interactions in all of those structures and what they were. And they come up with these plots where the size of the letter indicates how frequently that interaction is seen. And using that information, you can piece together a homology model or a guess, an educated guess at what your system should look like. So if you've run a simulation and you're not sure whether or not it's right, you could look in the protein database for related structures and see if it agrees with them. And to do that, you might want to talk to bioinformaticians or homology modelers or protein experts, or ideally, or the experimental team that works on the system that you're interested in. So you need to get out of your comfort zone if you're a biomolecular simulator, because if you're a chemist, you need to know about the physics and you need to know about the computing. If you're a physicist, you need to know about the chemistry. If you're a biochemist, you probably need to know something about the physics and the computing. These are the things that you're going to have to learn. So you're going to have to get out of your comfort zone. So it does not matter if you go to a presentation or a conference or a workshop and you don't understand all of the gory details. So I have been to talks as a physicist that look like this slide. So this slide is a synthesis slide. And what the chemists like to tell you is so these things here are telling you all of the things they had to do to get from this compound to this compound, and they tell you what percentage yield you've got, and they'll often tell you as well, you know, if there are difficulties like there's a chiral center that you need to be careful of, and all of that sort of thing. And you know, you cannot possibly understand it unless you're an expert. But what you can understand, and what I was able to understand mainly by having a conference buddy and asking loads of stupid questions, is, you know, what are those people doing and why are they doing it, and why are those the challenging things, and just get a grasp about, at the highest level, what it's actually about. And I think so certainly I have a, like, the chemistry is one thing. The other thing I used to have a very, very big problem with, of course, was sort of supercomputing. It's full of, you know, huge numbers of different acronyms, and I used to sit through these technical talks about the supercomputing in the days of e-science, and I used to get through it by imagining what all of the acronyms would be if they were rock bands. And that's how I actually got through it, you know, sort of EG would be a bit like the Bee Gees and things like that. And that's how I survived, because I couldn't understand anything. But eventually, if you persevere, you do start to grasp these things, especially if you know, if you're at a conference and you find a conference buddy who's an expert in that field who you can ask questions. Ask lots and lots of stupid questions. Do try and expose yourself to things that you have absolutely no clue about, because eventually you do pick it up. So that is my advice. And that is everything that I know about chemistry and all of the mistakes that I've made in the past. So I do hope there are lots of questions. Thanks, everyone.